Hi everyone, my name is Yung-Chian. I am currently a master's student at National Tsinghua University. My topic is vertical integration of pressure, humidity, temperature sensors for CMOS-MEMS environmental sensing hub. This is my outline. Firstly, I will give a brief introduction of environmental sensor, and then point out my motivation and design concept. Then following up would be the detail of the fabrication process, and then I would give the measurement results. Finally would be the conclusion of this research. Let's start with the introduction. Environmental sensors have been extensively adopted in consumer products and industrial applications. As the rapid progress in wearable devices and IoT, environmental sensors have a growing trend in consumer products. In particular, pressure, humidity, and temperature are the basic information for the environment. Next, I would like to introduce some of common sensing mechanisms for pressure sensors and the humidity sensors. For now, piezoresistive and capacitive type are still the mainstream on the market for pressure sensor. A piezoresistive pressure sensor has advantages like good linearity, large output signal, and low cost. However, piezoresistive materials is sensitive to temperature and high power consumption compared with capacitive type. A capacitive type pressure sensors tend to have higher sensitivity, lower power consumption, and temperature independent properties, but suffers from the parasitic capacitance and nonlinearity problem. As for the humidity sensor, can be classified into capacitive and resistive types. The resistive type is easy to calibration and is with simple readout circuit, but with the disadvantage of temperature dependent. And the capacitive type has good linearity and low power consumption, but would affect by parasitic capacitance. Considering the submicron gap of CMOS platform is good for capacitive sensors and for high sensitivity and low power consumption, this study would focus on capacitive type for both sensing units. Next is motivation and design concept. The multi-layers available in CMOS process enable the design flexibility to enhance the performance of sensors. Moreover, CMOS-MEMS platform is promising for monolithically integrating different MEMS components and circuitry interfaces. As for the capacitive pressure sensor, mentioned in previous page, which has high sensitivity, is proved to be CMOS compatible and with the multi-layers of the CMOS structure, providing us design flexibility to fabricate the pressure sensor. Interdigitated electrodes only need single layer and which have been used for humidity sensors in previous research. Furthermore, in previous research has been demonstrated that the fabrication process is compatible with pressure sensor. This study takes advantage of multi-layer CMOS process and the in-house post-CMOS process to monolithically vertically integrate the pressure, humidity, and temperature detector for the environmental sensing hub. Here demonstrate the schematic graph of proposed device. The proposed device consists of a pressure sensor with change structure vertically integrated with a humidity sensor on top and a temperature sensor at the bottom to minimize device size. The two multiple pressure sensor array is designed for larger sensing signal. Next, we will enlarge the cross-section part to see more detail. Pressure sensor is vertically integrated with a humidity sensor on top. The etching channel is designed for the metal wet etching. Besides, to prevent the sensing gap between electrodes being sealed by Weileun C deposition, the etching channel is designed with a step structure and with enough distance to let the polymer seal the pressure chamber here away from the sensing gap. And at the edge of the diaphragm, we'll have change structure defined by metal wet etching to lower the stiffness of diaphragm. And here shows the cross-section of pressure sensor and humidity sensor. From AA prong shows the deformable electrodes and reference electrodes are formed by metal tube and polysilicon layer respectively, and the capacitive sensing gap between two electrodes is determined by metal 1. And there is another etching channel to create the space between diaphragm and humidity sensor. The channel is connected to ambient pressure from pressure sensing. As for the humidity sensor, the interdigitated type electrode have a small sensing gap and is easy for polyimide dispensing. From BB cross-section, we can see the temperature sensor at the bottom of the device and the step etching channel for sealing pressure chamber. Here is the dimension of pressure sensors and humidity sensor. It is worth noting that the trench structure is not totally surrounded at the edge of diaphragm. Corner area of the diaphragm is reserved for electrical routing to connect the pressure sensor array. And proposed humidity sensor is composed of interdigitated electrodes with a total size of 400 multiple 400 micrometer square and 2 micrometer sensing gap. Following up is fabrication process and results. First, we received the chip prepared by the TSMC standard CMOS process. Then proceed to metal wet etching and following up with laser drilling, opening pad, and wire bonding. Then the chip is ready for permanency deposition to complete pressure sensor fabrication process. Finally, PI dispensing and annealing, then we can get the humidity sensor. Left side shows the top view of vertically integrated sensors and the etching holes. Right side shows the zoom-in view of humidity sensor, and we can see the interdigitated electrodes have been successfully made. Here shows the cross-section view of the proposed environmental sensing hub. The interdigitated electrodes of humidity sensor can be seen on the top, and below the humidity sensor is the pressure sensor. The sensing gap is defined by metal 1 after metal wet etching process, with poly and metal 2 layer as sensing electrodes. The top space for diaphragm movement and sensing ambient pressure can also be seen in the figure. On the right side is the zoom-in of the edge of pressure sensing diaphragm. The change is made to lower the stiffness for better sensitivity. Next is the results of measurement. This is the measurement setup for the pressure sensor. The device is placed in the pressure chamber and is connected to the LCR meter to measure the capacitive change. A pressure controller is connected to pressure chamber for pressure control. The measuring pressure range is from 20 kPa to 120 kPa. Measurement results show that the sensitivity of proposed device with polyimide process is about 0.383 femtofarad per kilopascal, and the one without polyimide process is about the same level. Thus, we can see that the polyimide deposition process and the anneal process after deposition, which is for the fabrication of humidity sensor, has no much effect on pressure sensor's performance. Next, we move to the measurement setup and results of humidity sensor. The device is put in the test chamber and the device is connected to the LCR meter for capacitance measurement. The measuring humidity range is from 30 to 80% relative humidity, with a commercial humidity sensor as humidity reference. Measurement results indicate the humidity sensor could work successfully after fabrication process with a sensitivity of 2.025 femtofarad per percentage relative humidity, with some hysteresis effect which may be caused by the diluted polyimide with 5:1 ratio of NMP and the parallel deposition. Lastly, the device is put on the hot plate with testing temperature from 25 degrees C to 85 degrees C, and the signal of the temperature sensor is measured by multimeter. The diode type temperature sensor has the sensitivity about 1.6 millivolt per degree C. Finally is the conclusion of this study. This study presents an environmental sensing hub with vertically integrated pressure, humidity, and temperature sensing units. Measurement indicates that there is no significant influence on the pressure sensor sensitivity before and after humidity sensor fabrication process. The result exploits the commercial standard CMOS platform to vertically integrate different environmental sensing units to form an environmental sensing hub for footprint reduction. Lastly, I would like to thank CNN, TSRI, and MOST in providing the fabrication platform, facilities, and research funding. Thank you for your attention.